topic is one-sided limits. In the last lecture, we talked about how a limit, to understand a limit, we imagine an ant crawling along a function and trying to figure out where it's going to end up. So let's take a look at the function that I've drawn here. If you're the ant crawling along, and once again we'll draw this as our red fire ant. If you're crawling along from the left side of the x value 1 that I've drawn here, you would conclude that you were going to end up at a y value of 2. On the other hand, if you were crawling along on the positive side, the right side of the value 1, you would conclude that you're going to end up at the value 3. So it looks like we can't really say that we conclude that we're going to end up in any particular place. But that doesn't mean that there's no statement that we can make about this. What we can say is that we can talk about the left-hand limit and the right-hand limit, or you can think of it as the limit from the left side and the limit from the right side. So the description that we have here, the description of the situation that we have here is that we would say that the limit as x approaches 1, make that a little neater, as x approaches 1 minus, I'll explain in a minute what that means, of f of x is equal to 2, and the limit as x approaches 1 plus of f of x is equal to 3. So this is what is called the left-hand limit. This is what's called the right-hand limit. So this is what left and right limits are. If we simply restrict our view to approaching a value c from one side or the other, then we can talk about different limits on the different sides. Now, this is the notation that we use for this. For the left-hand limit, we use this notation here. We say as x is approaching 1 minus, meaning it's approaching 1 from the lower side of 1. This is 1 minus, and if we're approaching from the right side, in other words, from the higher side of 1, we write 1 plus. So it's actually fairly significant that we write the plus or the minus after the number, because if we wrote it before the number, we would just be talking about -1 or +1. Here in this case, the approach point is +1 in both cases, but we're sort of overloading this symbol minus and plus, these symbols minus and plus, to say that we're approaching from the left side or the right side. So I've just put up the notation right here, and once again we say the limit as x approaches c plus of f of x is the right-hand limit. They're also called the right side limit, or the limit from the right, and the limit as x approaches c minus of f of x is the left-hand limit, which we can also call the left side limit or the limit from the left. I'm not going to write that whole notation there. So how do these limits come up in practice? I know I showed a picture, but I didn't really show a function. Typically, they come up in a couple of different contexts, one of which is case functions, or what are also called piecewise functions. The other one that we'll see shortly are functions involving absolute value, and as we saw in the pre-calc unit, every absolute value function really is implicitly a piecewise function. It's just sort of defined differently. So let me just show you what I mean here. So let's let f of x equal this piecewise function. It's equal to x plus 1 for x is less than or equal to 1, and is equal to 5 for x is greater than 1. So let's see. So let's just graph the function quickly. And let's see, 1, 2, 3. We'll just put those in. So this function is x plus 1. There. It's the function x plus 1 for all values of x that are less than or equal to 1. So this function looks sort of like that. And then put in these numbers here, 1, 2, 3, 4, 5. And then once you have an x value greater than 1, the function looks like this. So okay, so this is our function. And what you can see, it's sort of easy to see now graphically what's going on. If I'm the ant and approaching from the left, then we would conclude that we're going to end up at a y value of 2. If I'm the ant approaching from the right, we would conclude that we're going to end up at a y value of 5. So we can look at this and write that the limit as x approaches 1 minus of f of x is equal to 2, and limit as x approaches 1 plus of f of x is equal to 5. Now, you might wonder, how do you even get here analytically? The key to understanding this is that once we know which side we're approaching from, we can actually restrict this function to just one of its definitions or the other, essentially removing the other case. So if you look at x approaches 1 from the negative side, notice that we only care about the part of the function that's over here, which means that I'm not really worried about what the function does up here, because that has nothing to do with what the ant would see from the left side of x equals 1. The ant who's approaching on this side is only going to be looking at what the values of the function are approaching from the left, which is the diagonal part of the function. So therefore what I can do is I can actually do it analytically like this. I can say the limit as x approaches 1 minus of f of x is equal to the limit as x approaches 1 minus of the definition that only applies from the left side, which is x plus 1. Well, that's a polynomial function, which by previous rules we know we can just evaluate that by substitution. So that's just going to be 1 plus 1, which equals 2. On the right side, I can say the limit as x approaches 1 plus of f of x. Now I can ignore anything that's happening over here on the left side, and I can focus only on what the function's doing on the right side of 1, which is up there. So the limit as x approaches 1 plus of f of x is equal to the limit as x approaches 1 plus of the constant 5. Why? Because that's the definition for all values that are to the right side of x equals 1. Well, we know the limit of a constant, that's just a type of polynomial function. By substitution, that's just equal to 5. So that gives us the same result analytically, rather than having to draw the graph.